Okay. So last section in chapter 7 is 7.6. Mostly equations, but and identities, but we might look at a few inequalities. Usually inequalities we do on the calculator. Okay? Unless it's something very special that we could do by hand. So, the different techniques that we're going to be using to solve equations like that are factoring, quadratic formula, and trying to rewrite everything with one trig function. Having multiple trig functions in the same equation is like having multiple letters in the same equation. And you can't really do that. If you're going to solve a quadratic equation, this is technically not a quadratic equation, right? Because you got different variables in there. If it was y squared plus 3y plus 2, okay, now it's good. Otherwise, you have to get everything the same. All right, so as far as kind of explaining stuff, that's pretty much it. We just have to kind of look at some problems and try. So here's our first one. So first thing they write in the directions are find all solutions from 0 to 2 pi. So once we find the answer for x, are we putting plus the period times n? No, we're not doing that. Okay, so first thing we have to do is look at that and kind of decide what it kind of looks like, and if it's close, we got to make it closer. Okay, that's close to a quadratic. It's not a quadratic, but it's kind of close. The problem is we have two trig functions that are different. So anytime that you have an equation like that, you want to try to get it all in one trig function, substitute for the variable that is squared. Because you have Pythagorean identities that will allow you to change that into something with signs and a 1. So that's going to be our first step. Use this Pythagorean identity, which I won't always tell you, but for the first one I did. Use that to substitute in for that. Everything else is going to stay the same. Plus sine x plus 1 equals 0. Okay. What can you substitute in the parentheses for cosine squared? Yeah.
1 minus sine squared.
Yes. Any question on that?
So where'd you get that?
That comes from the Pythagorean identity. Right here. So that's something you're getting from section 7.4. Okay. Now what I want to do is distribute and combine like terms. 2 times 1 gives me how much? 2. Plus 1? 3. So I'm going to put that at the end. So I'm going to have a plus 3. I'm going to do that. That's negative 2 sine squared x. And the distributive property has nothing to do with sine x. Okay. Any questions so far? Yeah.
Okay, I see that we're using Pythagorean identity. Why are we using a Pythagorean?
Because you can't solve an equation that has different trig functions in it. So if you've got cosine squared and a sine, that's like having x and y in the same problem.
Okay, so you just find you just
Substitute always for the one that's squared. Okay. You don't want to substitute for sine. You want to substitute for the one that's squared. Okay. If we have, well, yeah, we'll just leave it at that. Substitute for the one that's squared, unless I say something else. Okay. So this equation that you have right here is basically like this equation. If you can solve that, you can solve the one above it. They're pretty much exactly the same thing. The problem is, if I was going to try to solve this equation, what do you think I don't like about what's in that box? The negative where? Yeah, if I'm going to try to factor, I don't know if this is factorable, but everything we've learned about factoring from Algebra 1, you never factor when the leading coefficient is negative. You always make that positive. So what we can do is divide everything by -1, and we're going to do the same thing here. Now, if this isn't factorable, then that's a waste of time. Maybe we should just go right to quadratic formula where A is -2, B is +1, and C is +3. Okay? But if it is factorable, then we can avoid quadratic formula, which, if we can, I'd rather try to do.
So, did the signs just cancel? That's what happened?
Did the signs cancel?
Yeah, why did you just write that what you just erased?
Just to show that if you could solve what I erased, it's the same as solving pretty much what's above it.
Oh.
So I'm just trying to show you that they're similar.
Oh.
Alright, so let's divide everything by -1. Minus sine x. Okay. Now, if it confuses you to try to factor it like that, then write this problem down and factor that instead. And once you factor that, just don't forget in the end, replace all your x's with sine x's. Okay? But let's see if we can factor it with the sine x's, if it's factorable. What would have to be my first term in that parenthesis? Two sine. Yep. And what about here? Sine. That's like 2x and x. Because if you multiply with FOIL, 2 sine x times sine x, it's 2 sine squared. Now, what would my signs be? I have a negative constant and a negative middle. Negative and positive, it does matter which one goes where. Let's try negative, positive. If that's wrong, we'll fix it. And then two numbers that multiply to give me 3. 3 and 1. We'll just try it in that order, see what happens. Okay. What's 2 sine times -1? Negative 2 sine. And what's 3 times sine? 3 sine. What's -2 plus 3? It's +1 sine. I wanted -1 sine. So what do I have to do? Just flip the signs. Now we get +2 minus 3. +2 minus 3 is -1 sine. -3 times 1 is -3. So that one was factorable. Okay. Once you factor it, what do you do with, this is factor 1, this is factor 2? Set each one equal to 0. And now from here, it's stuff we've seen before. 2 sine x minus 3 equals 0. Sine x plus 1 equals 0. Let's start with the one on the left. What would be your first step? Add 3 and then divide by 2. Okay. And now my last step to get x by itself. Inverse sine. So x is the inverse sine of 3 over 2. Now, what's 3 over 2 as a decimal?
1.5.
1.5. And if you graph the sine function, how high does it go? 1. That's higher than the sine function goes. So what do you think is going to happen? That's going to be a no solution from this part. If you didn't remember, just type it in and watch what happens. Second, inverse sine, 3 over 2. Remember, 3 over 2 is 1.5. The sine function doesn't go that high. You get an error. So from this part, there's no solution. Doesn't mean the problem doesn't have a solution. Maybe the other equation will work. So let's try that. How would you get x by itself here? Subtract 1, and then inverse sine. Inverse sine of -1. Now, does sine hit a value of -1 somewhere?
Yeah.
Then that one will work. Normally what I would do is do inverse sine -1. I can probably do it quicker Just thinking about that. Where do you hit -1? 3 pi over 2, or if you wanted degrees, that's 270. Now, remember that they said to only find answers between 0 and 2 pi, which that number is. 270 is between 0 and 2 pi, or 0 and 360. And that's the only answer that we get. 3 pi over 2. If you did this on a calculator, because you didn't know what the inverse sine of -1 came out to. Right, I'm in degrees, so I'm just going to do it that way for a second. Inverse sine -1. And you write down -90. Would you be correct in this problem? No. It's not that -90 is wrong. It's that they didn't want that answer. There's an infinite amount of answers. So they wanted between 0 and 360. So what can you always add to an angle that doesn't change it, it just moves it to the next cycle? The period, which in this case is 360. And there's your answer of 270. Right? Now, even worse, if you did this in radians, right, what's going to happen is you're going to get -1.57. You type that in. Now, -1.57 is this number. It's -pi over 2. But most of the time when you do it in radians, you get a decimal you're not going to recognize. So anytime that they ask me to do radians, I always do degrees first. Because a lot of times the degree answer will come out nice. And then if I have to, I'll take the degree answer and convert to radians manually. Right? Because I don't recognize decimals on the calculator usually when they're in radians. There's too many weird ones to recognize. All right. So that's my advice. Do it in degrees first. And let's say you got an answer like 40 degrees. But they said to write it in radians. Just multiply by pi and divide by 180. And that's how you convert it to radians by hand. So in this case, it would be like 2 pi over 9. You're never going to recognize the decimal. Whatever you get for 2 pi over 9, you're not going to recognize that as a decimal. That would have been 2 pi over 9. Unless you do degrees. Alright, let's try this one. This time they don't really say degrees or radians. They say find all solutions in one period. So, sine squared, period of that is pi. Okay, how do we know that? I gave you guys a chart that had trig functions, and it had even or odd powers. Your formula you always use is pi over b or 2 pi over b. This formula, sine to an even power, the formula is pi over b. And where do you find b? Whatever's in front of x. So the formula for this is technically pi over 1. This is cosine if you want. Think of it as cosine to an odd power. The formula for that is 2 pi over b. What's the least common multiple of those two periods? 2 pi. So when they ask for all solutions within one period, you're finding them from 0 to 2 pi or 0 to 360. However you want to do it. Let's do 0 to 360. If this one came out to pi and that one came out to pi, then I'd be doing 0 to 180. Okay? I'm doing the LCM of the periods. Just like when we graphed, we had to find the LCM. Okay, is that a quadratic equation?
No.
Not quite. Couple things wrong with it. Usually when you want to solve a quadratic, what do you get it equal to first? This one already was. So let's get this one to the step that the first problem was at. And I'm going to put everything on the right. Okay. Now, you might be thinking, why do you move everything to the right? Because if you look at the sine squared, I told you when you try to factor, use the quadratic formula, you want the squared term positive. So you might think, we'll just leave the sine squared on the left. But let's try putting it on the right and see what happens. Okay? So let's get that equal 0. That's -2 sine squared x plus cosine plus 1. Okay. Any question on the first step? All right. Now, it's like we have two different variables here. You got two different trig functions. Which one are we going to substitute for?
Sine squared.
Yep. And what's the identity that we're going to use to substitute?
Sine squared plus cosine squared equals 1.
Yep. I'm just going to put that right here. So the identity, sine squared plus cosine squared equals 1. So just leave that space there. Plus cosine plus 1. What is sine squared?
1 cosine squared.
Yes. Does anybody see now why I put everything on the right? Because when I distribute, negative times a negative is going to make that cosine squared positive. Had I left everything on the other side, I would have had to divide by -1 and fix it. It's not a big deal. But this saved me a step. Okay? So anytime you substitute for a squared function, the positive negative value of it is going to become the opposite. It started as negative, it's going to end up positive. All right, so let's distribute. What's -2 times 1? Plus 1. So we got -1. -2 times negative cosine squared just became positive. And plus cosine. Okay. Now, is that a quadratic type of problem? Yes. As long as this is squared, that's to the first power, and they're both the same, cosine, cosine, that's a quadratic kind of problem. In fact, anything like this, something to a power, plus or minus something to that power, plus or minus a constant. That's a quadratic type problem. The idea is this exponent has to be double that exponent. So if it was a 6 and a 3, that would be a quadratic kind of problem. You could use the quadratic formula. If that was a 12 and that was a 6, yep, you could use quadratic formula. As long as there's exactly 3 terms, that exponent is double that one, and the last term has to just be a number, like 7, 12. Anything that fits that pattern. Great. So let's look at it and see if it's factorable. Right? For me, sometimes it's easier to just think of this and see if I can factor that. So I'm going to do this one trying to factor it like that, and if I can do it, I'll change my x's back to cosines in the end. Okay. So what would have to be your first term? This term? What about your sines? Well, they got to multiply to give me a negative. So it's got to be one of each. And 2 numbers that multiply to give me 1, I don't have any choice. Let's check that. That's 2x minus x. Is that what I wanted? So 2x times 1 is 2x. -1 times x is -x. Add them up. Yeah, that's what you wanted. 2x minus x is plus x. -1 times +1 is -1. 2x times x, 2x squared. So we factored it. Perfect. So that's not really our problem, okay, because we took the cosine out. Our problem is really 2 what? 2 cosine. And what about the other factor? Plus 1. So this one I did a little different, just showing you can factor it with the x's and then change it back after. Depends what you're more comfortable with. Questions on that? Okay. So here, what would cosine x equal if you had set it equal to 0, this factor, and got the cosine by itself? 1/2. And let's do this one. Cosine x equals -1. Okay, what do we have to do on both of them? Take the inverse cosine. Inverse cosine of 1/2. Now, here let's do that first and see what happens. Inverse cosine of 1/2, and I think I said I'm doing it in degrees. So we're looking for answers between 0 and 360. Put it in degrees. Second, inverse cosine of 1/2. You're going to get a nice answer, 60. What quadrant is that answer in? It's in the first quadrant. If you're looking for where cosine equals a positive number, which we are, where cosine equals positive 1/2, on that coordinate plane, how many quadrants does that happen in? 2. It happens here. And where else is cosine a positive number? 4. You have that answer, 60. That's your reference angle. If you're in quadrant 4, what do you do with your reference angle to get an answer in that quadrant? Quadrant 2, you do 180 minus. Quadrant 3 is 180 plus. What do you do in quadrant 4?
360 minus?
360 minus, yes. So your other answer is 300. Very easy to check if those are right. Take the cosine of 300, see if you get a 1/2. Cosine of 300? Yep, gives you a 1/2. Take the cosine of what you think the other answer was, 60. Yep, it's a 1/2. So what you're basically doing here is think of the graph of cosine. It goes like this. Think of a line at 0.5. 0.5 is right here. You're finding both the intersections without graphing. Okay? You found the one in the first quadrant, and then you found the one in the second quadrant. And those are the 2 answers in that cycle. Okay, any questions on it? Yeah, and the other one's going to be easier because anytime it's equal to a 1 or a -1, you only get one answer. All right, so here, inverse cosine of -1. Now, actually, I already have the graph there. Where does cosine hit -1? 180. Yep. So this problem has 3 answers. 60, 300, 180. And you don't have to put plus the period times n because they said not to. They said just 0 to 360. Okay? This is the part that some people forget about. So they get the 60 and then they forget to get the 300. So you do have to look for that second answer. If the second answer would be in the criteria they asked for. If the second answer was like, it would have never been this, but let's just say it was 410. Well, that would be outside what they said to look for. So then you wouldn't need it. But that wouldn't happen in this problem. Okay. Any questions on that? All right, let's try. Well, actually, I'll just review that quickly. So, if instead of saying find the answers in one cycle, they say find all solutions. We've done this in a few sections. Find the solutions just like we did in the last problem, but then put plus the period times that. Any questions on that idea? That's only if they ask for all solutions. In general, I'm not going to have you do all solutions in this section. Okay? I want you to remember that there are infinitely many, but we've done that before. So we're not focusing on representing plus period time then. Okay. We're gonna do it like we did the first two. Okay. Let's try this one. Find all solutions from 0 to 2 pi. It's nice when they give you the interval, because then you don't have to worry about finding LCMs and all that stuff. They told you, 0 to 2 pi. Is that a quadratic equation? It will be. We just have to figure out how to make it. Any thoughts on what I could substitute for here? Well, which trig function there is more complicated and can be written in a simpler way? Tangent, right? Sines and cosines are the basic trig functions for everything. So let's try to take tangent and make it simpler and see what happens. How can you rewrite tangent? Okay. So you can write it as sine over cosine equals 3 cosine. Is that a quadratic equation? No, quadratic has to have something squared in it. So, anyone think they know what the next step would be? And this is going to make something squared, and then this is going to turn into that part.
You have to multiply by the cosine.
Yep, multiply both sides by cosine. That's gone. Now you have sine x equals 3 cosine squared, just like the last two problems now. Okay. That's almost a quadratic equation. What side should I put the cosine squared on? If I want it positive, I should put it on the left. If I ultimately want it positive, okay, put it on the left. So that's going to give you negative 3 cosine squared plus sine equals what? 0. Now, which trig function do you always substitute for in this kind of situation? The squared one. All right. So our ID we're going to use sine squared, cosine squared equals 1. What's cosine squared? 1 minus sine squared. Okay. Plus sine x equals 0. Okay. Let's do our constant. What's negative 3 times 1? Anything to combine it with? Nope. So let's just put that there. Negative 3 times negative sine squared. That's why we put it on the left, so now it's positive. Plus sine x. Now, this one I can tell by just kind of looking at it quickly and doing lots of factoring that you cannot factor that problem. That's not factorable. So if you can't factor it, what do you have to do? Quadratic formula. So it's the first one we've had to use that for. Takes a little longer when you got to do quadratic formula. There is no guesswork in the formula. Factoring sometimes is a little guesswork, but you know, I still prefer factoring because I think it's quicker. So what's A in this case? 3? B?
1.
C. Now, remember, when you have a quadratic formula, you usually have like something, I'll just do the basic one, something squared, plus something, plus a constant. And if you just fill in something like that, what are you solving for normally when you use quadratic formula? Solving for whatever is in that box, which in that case would be x. So, when we use quadratic formula, we are solving for whatever would be in that box. Okay? So you're not solving for x. What are you solving for? Sine x. So you're going to use quadratic formula. And whatever you get for an answer, well, I'm not going to put a box because that won't be the final answer. But whatever you get from the quadratic formula, put it there and put it there. Because it's not x, it's sine x. So it's the only extra step to using the quadratic formula with a trig equation. You're solving for whatever that box is in that box. So let's go through and do it. All right, so we get -1 plus or minus the square root of 1, 4, a, c. Would have been nice if that -3 was a +3, then we would have had imaginaries and we could have just stopped. But it's not going to happen. All over 2a. All right. Minus a minus, what happens there? We have -4 and then the -3. That's going to become a positive. And what's 4 times 3? Plus 3? Sorry, 4 times 3 is 12 times 3.
36.
Plus 1.
37.
So now you can see it was never going to factor. If it factored, you would have gotten the square root of like 25 or 36. You would have gotten a nice number. Right? All divided by, is that x? That's sine x. So put that right here. Negative, and I'm going to write it as two separate things instead of plus or minus. Plus square root of 37 over 6. And -1 minus square root of 37 over 6. Okay. So what do we have to do on each one? Inverse sine. So we'll take the inverse sine. If we get one answer, you've got to use the ASTC chart to look for the second answer. So let's try inverse sine. -1 plus square root 37 over 6. All right, let's go -1 plus square root of 37. It's 5.08. Divide that by 6. 0.84. Is 0.84 a value in the highest to lowest that sine goes? Yeah. So that when I do inverse sine of that number, it's going to be okay. So let's go second inverse sine of, and I can just do the last answer that was on the screen. Now, I'm still in degrees, which is fine if we're doing it in degrees. But they said radians. So let's change to radians before I hit enter.
I thought you want to do degrees.
Because this is not going to come out to it. If it's factorable, I would say yes, because you're going to get a nice answer. You're going to get an awful answer no matter which way you go. So if you have to use quadratic formula, that doesn't help. But that's a good point if it's factorable. Okay, so one answer we get is 1.01 radians. Right, so let's think of our chart. When I did all this out, -1 plus root 37 over 6, I got 0.84. This is 0.84. Right there. We're looking for where sine equals a positive number, 0.84. How many quadrants is sine positive? 2. Here and here. Little trickier with radians to figure out your quadrant because it's not as nice as like 0, 90, 180. But remember, this is 0. This is 90, which is what? In radians. Pi over 2, which is 1.57. How about this one? Pi, which is 3.14. And this one? It's 3 pi over 2, which is 4.71. 1.01 is in which quadrant? Okay. So you have an answer in the first. What's the other quadrant you're looking for an answer in? Second. What's the formula in quadrant 2 once you have your reference angle? Minus it from what? In degrees, yep. What about minus it from pi? So it would be 180, but this is radians, so it's pi minus 1.01, and we get 2.13. Okay, so there's our answers there. Now, we could potentially get 2 more answers. Let's see what happens. How would you get x by itself on the right? Inverse sign again. Now, let's just do out what's inside the parentheses and see what we get. Like I got 0.84 over here. I want to see what happens over there. Because if I get a number that's beyond -1 to 1, I can just stop. Okay? If I don't, I got to go through all that stuff that we just did. So, we've got -1 minus the square root of 37. That's the numerator. When you divide that by 6, what kind of number are you going to get? Negative 1 point something. That's beyond -1. You can't take the inverse sign. If you try to, it's going to give you an error. So I can't do it. So there's no solution from this part. So those are my only 2 answers. But potentially I could have had up to 4 in this problem. Okay. Any questions on that? There's really not a lot of new stuff in this section. It's tying together a bunch of stuff that we've learned. The ASTC chart, all this stuff. Quadratic formula, some stuff in algebra.
So why is it okay that like 1 is over like
Because this part that's circled came out to 0.84.
Oh, okay.
If you get a number between -1 and 1, you can take the inverse sign of it because it's in the domain. If you get a number beyond -1 and 1, you can't. These 2 numbers, that's just what the answer came out to. That's all.
So how do you go from 0.84
I took the inverse sign of 0.84.
Okay.
And I used it as an exact, 0.84, whatever it is. Alright, this one's kind of the same thing. It's actually easier than the last one. You just get everything on one side, use the quadratic formula. Or factor it if you could. Any questions on this type? So we're not going to do another one of those. Let's try this one. Okay. So find all solutions in one period, and they're telling you that the period is basically pi, or 180. They're having you find all the answers between -90 and 90. So you don't have to worry about the LCM. Most of the time, you're not going to have to, because it's just too many things to remember. There's already a lot to remember. Okay. So, is that a quadratic equation? No. But is one exponent double the other? Yes. So then we might be able to make that into a quadratic equation if we can get the same trig function everywhere. Right? There's an identity that involves these. It's like sine squared plus cosine squared equals 1. But does anyone remember the Pythagorean identity that has tangent squareds and secant squareds?
Isn't it 1 minus secant squared equals tangent squared?
Maybe, I never remember it that way. Yes. 1 plus tangent squared equals secant squared, or what you said. This way is going to be better. You'll see why in a second. Right? So, when you have a problem like this, and you're trying to make it a quadratic, which one did I always say to substitute for? The squared one. So we're going to focus on secant squared. Now, I also know it's not equal to 0 now. We'll worry about that. So 1 plus, using Pythagorean identity, so this is an identity. What is secant squared? 1 1 plus tangent squared. Okay. So what do I have on the right when I combine like terms? 2 plus tangent squared. Okay. Alright. Now it's starting to look more like a quadratic, except usually we get a quadratic equal to 0. And we like the highest term, the leading coefficient, to be positive. So we've already converted everything. So let's put tangent squared on the left. So you're going to have this. And how would you move tangent squared to the left? Subtract it. And let's move the 2 to the left. Yep, subtract it. Okay. So now what you're trying to factor is this. Might be easier because sometimes you just get confused when you see tangent. Pretend it's not tangent. Pretend it's just x's. Let's try to factor that. What would have to go as my first term in the first parenthesis? 3x squared and x squared. Okay. Signs would have to be what? A plus and a minus. Could be a minus and a plus. And two numbers that multiply to give me 2. 2 and 1. Let's check it. 3x squared times negative 1. 2 times x squared. Negative 3 plus 2. Is that what we wanted? Perfect. So we just factored it. But our version really is going to replace x with what? Tangent. So 3 tangent squared plus 2 and tangent squared minus 1. Now, what do we do with each of those factors? Set them to 0. Let's do the right one first. No, let's do the left one. Watch what happens when you do the left. Try to do the easy one first to show you what happens. How would you move the 2 and then 3? Minus 2 divided by 3. Now, you can't do inverse tangent yet, because there's something else you have to get rid of first. Take the square root of both sides. Square root, square root. That and that cancel. So now you have tangent x equals the square root of negative 2/3. So what happens there? The inverse tangent of that? Well, let's just type that in first and see what happens. Right, it's imagining. You can't do that. If you ever have to take the square root of a negative, you can forget about the solutions from that part. Okay? If the negative wasn't there, like if this was a minus 2 when we factored it, then this would have been okay, because it would have been a plus 2 when I moved it to the other side. But because it's the square root of a negative, you can't do it. Any question why the left side is done? Okay. So now all we have to do is look at the right factor. What would tangent squared x equal on the right? 1. Now can you take inverse tangent? Take the square root first. Square and square root cancel. And what's the square root of 1? And negative 1. So we get 1. You could write it like this. So two things you have to check. So I would rather just write them separate. Tan x equals 1. Tan x could equal negative 1. Questions on why we get 2 answers from that square root? A lot of people miss them. They get 1 answer, but then they forget, oh, the square root of 1 is also negative 1. Now, what can I do to each of these? Now you can do inverse tangent. Inverse tangent of 1. Inverse tan And what did I say about if you can factor it, what unit should you try first? Try degrees first because usually you get a nice answer. Okay? Not always, but usually. If you have to use quadratic formula, you almost never get a nice answer. That's the whole point.
Why don't you want these ones to be in sine and cosine?
Because this whole original problem didn't have any sines or cosines in it at all.
Oh.
So if you don't have any sines or cosines to start, you may not be using any sines or cosines. This one it just happened to be tangents. All right, so let's finish up this one and then we'll stop with that one. All right, so second, inverse tangent of 1 gives me 45 degrees. I'm going to come back to this in a second. Let's do the other one. Inverse tangent of negative 1. It's going to be negative 45 degrees. Now, we were looking for where, let's start with this one. Tangent is a positive number. Tangent equaled 1. How many places is tangent positive? 2. Here and here. Where's 45 degrees? What's your formula to get an answer in quadrant 3? 180 plus. So I'm going to put this down here for a second, but I have to see if 225 was what they told me they wanted the answers between. I don't think it was. Right? Let's just do, just to make it simple, negative 90 to 90. Is 225 an answer that I should leave there? No, they don't want it. For whatever reason, they don't want it this time, so I'm not even going to write it. Okay, let's check the other one. We've got negative 45. What quadrant is that in? Right there. Where else is tangent equal to a negative number? Here. All right. So your reference angle, remember, the reference angle is always positive. The reference angle is 45. What's the formula in quadrant 2? 180 minus 45, that's 135. Go back up. Did they want 135? No. They wanted negative 90 to 90. So I don't even need to write it. So that ASTC thing in this problem, it's a waste of time. They don't want it. This is all they want. So every problem in this section boils down to a quadratic. Every single problem. This is a quadratic as well. Okay, quadratic or quadratic type.
So it's only used, the SATC thing is only used as adding additional answers, right?
It's to get the additional answers, yep. But when you get those additional answers, make sure that the original question wants them. If they don't want them, don't write them. All right, so we finished, I'd say like 80, 85%. We'll finish the rest of 7-6 tomorrow. So, homework. It's not going to be that. 1 through 6 is fine. 7 through 10, that's fine. In some of these problems, they set the whole thing up for you. Every problem I did in class, you had to set the whole thing up from scratch. Okay? So you'll see in the homework, some problems are already factored for you.
So it's 1 through 10. So you said 1 through 10?
1 through 10 is good. Definitely can't do. Hold on. Let's just do 1 through 10. And then I'll do the rest tomorrow.